A different reason is the parallelizability of the quantum algorithm is different. So classically, you can take this big search problem and just partition it up into however many GPUs you want to buy, and you get a speed up, a linear speed up. If you buy twice as many computers, it speeds it up by a factor of 2. Quantumly, if you buy twice as many computers, it doesn't speed it up by a factor of 2. Right. So if you buy P quantum computers and you partition the search space between your quantum computers, then you have 2 to the 256 divided by P, so your search, each of them has to search that much space. So you take square root of that is the amount of time you need to run them. And so overall you get, that should be an 8, maybe it is, 2 to the 128 over square root of P instead of over P. And it's just a small difference, but it's a difference. You need to buy quadratically many quantum computers to get the same speed up. And finally, of course, so even this kind of thing is very optimistic because you also have an overhead from fault tolerance because you got to do error correction on top of these quantum computers. So these people studied it, for example. They studied the cost, including error correction. I imagine this can be improved by many orders of magnitude, but this is their approximate, probably. I don't know, this is from 2016. Probably you can, if you study it carefully, you can improve it by at least a few orders of magnitude. But still, so they're up to, so they're using 2 to the 12 logical qubits, whatever that is, a few thousand. 2 to the 153 is the time. And yeah, anyway, so they studied it carefully for SHA-256 and SHA-3-256. This is a variant. It's a little bit harder.
275 billion times more expensive.
Our results suggest that executing these attacks may be as much as 275 billion times more expensive than one might expect. Okay, because of the overhead from fault tolerance, I guess. So now there's lots of papers that study the different. We can talk about this later when we get about different architectures. But this is just a table that compares different times and stuff for different architectures. I'll talk about that later. So this is one application of Grover search is just to get a square root speed up. And it's not a huge deal. I mean, if it were a big deal, you could just like make this 512, right? And it's not going to be that much slower. But it's not going to be that much slower to evaluate, but it will make the complexity that much harder, even on a computer. Probably. If we think it's hard, something else. Right. Good. All right, so let's see some simple examples of applications. So here's a problem that's called the collision problem.